Sound insulating constructions. Wall constructions. Wall constructions are broadly classified into two types, wet and dry. Wet constructions include blockwork, brick and concrete, and dry constructions or dry walls consist of plasterboard, medium density fibreboard, fibre cement sheet, or any combination of these materials. The building industry is steering away from the widespread use of wet walls wherever possible because of the time to construct, the difficulty to construct, the cost of construction, and work safety problems associated with lifting heavy blockwork. Wet walls are usually restricted to facades where environmental damage from rain and wear and tear would quickly destroy drywall partitions. Drywall partitions for internal walls of buildings are also removable at a later date, and this gives added flexibility for space planning and for refits of buildings for other purposes. Airborne sound insulation performance is measured in terms of the weighted sound reduction index. RW, or the sound reduction index, is a single number rating which denotes the sound insulation performance of a wall or a floor partition in decibels. It's determined by comparing the measured sound transmission loss, or the sound insulation performance, in third octave band frequencies to points on an RW reference curve. As you can see on the right-hand side here, the grey dots are the measured sound transmission loss, or the reduction in sound from one side of the partition to the other, in different third octave bands. As you can see, the sound insulation performance is much higher at those mid to high frequency bands than it is at the low frequency bands. And again, this is because of the wavelengths of sound compared to the thicknesses of these materials used to stop sound from passing from one side of the partition to the other. And as you can see, that black curve is the RW reference curve. So when you plot the different sound insulation measurements in different third octave bands against this reference curve, you can then determine the overall RW value. Sound transmission class, or STC, is the alternative measure used in the US to the RW, or the sound reduction index. Again, it is a single number rating used to compare the sound insulation performance of partitions for general design purposes. It uses a different reference curve to compare the measured sound transmission loss in third octave bands to points on an STC reference curve. Limitations of single number ratings. So there's a word of warning for using RW and STC in isolation without considering the different third octave band sound transmission loss performance. Since the RW and STC are single number ratings based on third octave band levels, they don't give you an indication of the sound insulation performance of partitions, walls, or floors for sound sources which contain predominantly low frequency sound or tonal sound. For example, RW does not consider sound below 100 Hz, so it does not consider low frequency sound transmission. Single number ratings such as RW and STC should therefore only be used in preliminary design stages. Once you get through the scheme design stage, you then have to start looking at the different third octave band performance of different partition build-ups or floor build-ups to ensure that low frequency sound transmission is adequately dealt with. Another word of warning about laboratory measured data versus field performance. The RW and the STC are determined in a laboratory controlled condition. When a partition is installed on site, it usually does not achieve the specified STC or RW because of flanking paths or weaknesses and inaccuracies with the construction methods. A rule of thumb for determining on-site performance of partitions is to subtract 5 decibels from the laboratory measured rating to account for installed conditions. So for example, if a wall partition gives you an RW 45 sound reduction, on site you could only expect to get a site-corrected RW or R-W of 40 decibels. This should be accounted for in the design stages to make sure that adequate sound insulation can be achieved by the wall and floor partitions that are being specified. Let's look at some different wall constructions and the RWs that they achieve. First of all, RW25. So this means 25 decibels reduction from one side to the other. The wall build-up needed to achieve RW25 includes one layer of 10mm standard plasterboard, a 64mm steel stud in between, and another 10mm layer of plasterboard on the other side. It's important to consider how high the partition goes, whether it goes to the ceiling line or to the full floor-to-floor extension of the wall height. And in this case, at an RW25, the partition would only extend to the ceiling line with a plasterboard ceiling. Alternatively, you could get RW25 out of a 6mm thick float piece of glass. To achieve RW35, you would need a layer of 13mm plasterboard either side of that 64mm stud, or you could achieve it with a 10.38mm laminated piece of glass. Again, the floor to ceiling extension of the partition would be adequate to achieve RW35. There's no need to go floor to floor or slab to slab. To achieve RW40, you could use one layer of 13mm standard plasterboard, either side of a 64mm stud, with 50mm fiberglass in the cavity. Or you could use a double glazed unit consisting of 10mm float glass, 12mm air gap, and a 6.38 laminated pane of glass, or one thick piece of laminated glass of 12.5mm thickness. To get RW45, this is where you would need a slab-to-slab construction. So the partition would have to extend the full height between the different floor slabs in the building. To achieve RW45, you would need a layer of 16mm standard plasterboard, a 64mm steel stud, 40mm fiberglass in the cavity, and 2 layers of 16mm standard plasterboard on the other side of the stud. Alternatively, you could use higher surface mass sound rated plasterboard with 13 kilograms per metre squared per sheet. So one layer of 13mm sound rated plasterboard either side of that 64mm stud with 50mm fiberglass insulation in the cavity. Again, a full slab to slab height wall partition. You could also use a 10mm float glass, 16mm air gap, and a 12.5mm acoustic laminated glass. To achieve RW50, this is quite challenging to achieve with glazing. So in this case, you would need a 10mm float glass, a large 200mm air gap in between to a 6mm float glass. The framing is very important as well as the glass construction here. When you get to the high performance glazing systems, it's usually the aluminium framing system that is the weak link. So it's important to consider the surface mass of the aluminium frame and whether the frames need to be packed with a solid material to increase the mass. To achieve RW50 in a wall partition, you would need 2 layers of 13mm fire-rated plasterboard, a 64mm stud with 50mm fiberglass in the cavity, and then 2 layers of 13mm fire-rated plasterboard on the other side. And of course, again, you'd need a full slab-to-slab construction. To achieve RW55, we're getting into very high performance acoustic partitions here. We actually need to have separate studs or staggered studs. So instead of having one single stud connecting the 2 leaves of the partition, we now have to separate them to reduce that structure-borne sound transmission paths between the 2 sides of the partition. So in this case, to achieve RW55, we would need 2 layers of 13mm fire-rated plasterboard, separate 64mm studs offset in a 92mm track, 50mm fiberglass insulation in the cavity, and then 2 layers of 13mm fire-rated plasterboard on the other side. Using a wet wall construction, you could also achieve it by using 90mm solid block on either side of a 50mm air gap.